In the world of data, time series data stands out as a unique and fascinating category. It's a sequence of data points collected over time, where the order of observations is crucial. From tracking stock prices to monitoring weather patterns, time series data is everywhere. Imagine you're observing the daily temperature fluctuations in a city. Each day, at a specific time, the temperature is recorded, creating a sequence of data points ordered by time. This ordered nature allows us to analyze trends, patterns, and anomalies that unfold over time. Financial markets generate high-frequency time series data, with stock prices changing every second. By analyzing these temporal patterns, we can gain a deeper understanding of the underlying processes and make informed predictions about the future. Time series data possesses distinct characteristics that set it apart from other data types. The most significant of these is its inherent time dependency. In time series, the order of observations matters. Each data point is related to its predecessors and successors, forming a continuous flow of information. This temporal dependence introduces the concept of autocorrelation, which measures the correlation between a time series and its past values. For instance, tomorrow's temperature is likely to be correlated with today's temperature. Another key aspect is the presence of trends and seasonality. Trends represent long-term patterns, such as a general increase in global temperatures over decades. Seasonality refers to repeating patterns within a fixed time period, like the peak in ice cream sales during summer months. These unique characteristics necessitate specialized techniques for analysis and forecasting. Analyzing time series data presents a unique set of challenges that require careful consideration. One of the primary challenges is handling missing values. Missing values disrupt the temporal continuity and can significantly impact the accuracy of forecasting models. Dealing with missing values often involves sophisticated imputation techniques that consider the temporal dependencies within the data. Another challenge is dealing with outliers, which are extreme values that deviate significantly from the expected range. Outliers can occur due to various reasons, such as measurement errors or external events. Time series data can also exhibit non-stationarity, meaning its statistical properties change over time. Addressing these challenges requires a deep understanding of time series characteristics and the application of appropriate techniques. Section 4. Forecasting the future. Methods in time series analysis. Time series forecasting, the art of predicting future values based on past observations, employs a diverse set of methods. Moving averages, a simple yet powerful technique, smooths out short-term fluctuations to reveal underlying trends. Exponential smoothing methods assign exponentially decreasing weights to past observations, giving more importance to recent data points. For more complex patterns, ARIMA models, or autoregressive integrated moving average models, provide a comprehensive framework. ARIMA models combine autoregressive terms, integrated terms, and moving average terms to capture a wide range of time series patterns. Deep learning techniques, particularly LSTM networks, have gained significant traction in recent years. LSTMs excel at capturing long-term dependencies in sequential data, making them well-suited for time series forecasting. The choice of the best method depends on factors such as the characteristics of the data and the desired forecast horizon. Section 5. Real-world applications of time series forecasting. Time series forecasting plays a pivotal role in numerous real-world applications across various domains. In finance, it's used to predict stock prices, optimize investments, and manage risk. Retailers rely on time series forecasting to forecast sales, manage inventory, and optimize pricing strategies. Supply chain management heavily relies on time series forecasting to anticipate demand and streamline logistics. Weather forecasting is a classic example of time series analysis, where historical weather data is used to predict future weather patterns. These examples highlight the wide-ranging impact of time series forecasting on our daily lives. Section 6. Evaluating time series models. Measuring accuracy. Evaluating the accuracy of time series models is crucial to ensure reliable forecasts. Mean absolute error, or MAE, measures the average absolute difference between the predicted and actual values. Mean squared error, or MSE, squares the differences between predicted and actual values, giving more weight to larger errors. Other metrics, such as root mean squared error, or RMSE, and mean absolute percentage error, or MAPE, provide alternative ways to quantify forecast accuracy. The choice of the best metric depends on the specific application and the relative importance of different types of errors. Evaluating time series models also involves techniques like train test split to assess the model's generalization ability. Cross-validation techniques, such as time series cross-validation, are particularly useful for evaluating time series models with limited data. Section 7. Conclusion. The power and potential of time series analysis. Time series data offers a unique lens into the dynamics of our world. From understanding past trends to predicting future outcomes, time series analysis empowers us with valuable insights across various domains. Mastering time series data requires a deep understanding of its unique characteristics and the diverse range of methods available for analysis and forecasting. By embracing the power of time series analysis, we can navigate the complexities of a data-driven world and unlock a brighter future. The applications of time series analysis are vast and constantly evolving.